Welcome back to yet another video on our channel Euclid Mathematics. We have started lecture series on CSIR NET SET Gate and other competitive exams. So with that we learn all important subjects: linear algebra, real analysis, group theory, ring theory, calculus operation. All subjects we learn in our channel. So if you wanted to see these videos, these subjects, you may check it into my playlist. So in my today's video, I'm going to explain to you all one of the question from linear algebra, which asked in CSIR NET exam for 4.75 marks, paper third question. Now let's get started today's question. I'm going to explain to you all first of all the question, and then we'll go for understanding its solution. Here in my question we have given which of the following are eigenvalue of a matrix. Okay, and matrix given here 0 0 0 1 0 0. Okay, triple 4 0 1 0, again 0 0 0 0 0 1. Okay, and 1 remaining 0 0 1 0 0 0 0 and 0 0 1 triple 0 here. Okay, this is some special type of a matrix. If we are trying to find the inverse of a matrix by our regular method, I don't think so you will get the inverse in easy way. Okay, so we have to apply some of the standard results, or we have to identify which type of the matrix is this. So then after it is quite easy to figure it out. It's a true eigenvalue. Okay, now here we can see we have four options: first +1, -1, +i, -i. We have to figure it out which one of the option is correct, because question it is from paper third, 4.75 marks. Maybe one or more than one option is a true, and we know that one matrix is having more than one eigenvalues. Okay, so it is matrix how much rows, how much column here. It is a 6 column and 6 rows here. That means 6 by 6 matrix here. Okay, 6 by 6 matrix means it contains completely 6 eigenvalues. Okay, so let's get started on today's solution. I'm going to explain to you all a detailed understanding of our today's example. Here in example, we have given matrix, all entries 0, and every row contain one single time 1. Okay, so second row also contains single time 1, and third row similarly for all rows. Okay, every row contains single time 1, and every column it contains single time 1. Okay, so try to remember this is some special matrix like a permutation matrix. What we learn in our permutation matrix? Permutation matrix, it says that if we have every row or every column which is 1 at one time, okay, that means one row contain 1 at one time and remaining entries are 0, and only the entry which is in our matrix which is a 0 or 1. Okay, so we call it as the permutation matrix. And one more thing, if you know plus thing that a permutation matrix is having only two eigenvalue which is a +1 and -1, then you can easily say that option A and option B is correct here. Okay, permutation matrix do not have imaginary eigenvalue, so C, D option automatically eliminate. And if you don't know how to find the eigenvalue by our standard method in our linear algebra, let's get to find out our eigenvalue from our matrix. Okay, so in group theory, we learn one result. Okay, permutation matrix is similar like that in learning. We learn it in the group theory. Okay, like we learn in a permutation group that we have to take the mapping from one element to other element which associated with this element. Okay, so here we can see we have matrix which one column contain 1 at one time. Here we can see here also third element here, and here. Okay, so what we do in a permutation matrix, we first of all find out their images, and after getting images we take the LCM. Okay, so if I got the image like to A goes to B, B goes to C goes to D, D goes to E, something like these images, we always take LCM to find out the order of given given group. Okay, so we are taking LCM between this. After taking LCM, if he got the order of A, LCM suppose call it as the K. Okay, so if I got the order of A is a K, then we write A to the power K, then which gives a matrix, whatever we have matrix here. For example, if I consider B, it is matrix here. Okay, so we can write it here B to the power order of A. Order of A means which we have K, which is we get the identity. Okay, So this is the result we learn it into the group theory. The result says, I'm trying to explain it one more time. Okay, so if we have a matrix, so we want the element for some element order from there. Okay, so if I consider I want the order of A, so we take the order of A as a LCM of a different length of a different cycle. Okay, so we are taking LCM from the different cycle, and that if I got that LCM as a K, that means order of A which is equal to K, then we write the matrix to the power order of A, which is the identity. Okay, now let's apply this result in our linear algebra. Now see how these subjects are interconnected. If you know the result from group theory, you may solve this example in a quiet second. Okay, as this is a permutation matrix, we know the standard eigenvalue, but we are going to solve actual way to find out the eigenvalue for our matrix. Okay, now let's first of all build here the order pair where images of our element lies. Okay, so here we can see our first column, first element goes to fourth element. Why first goes to? Because first image it gives us 1, first goes to fourth. Now you can see first, second, third, fourth. First column it goes to fourth row, that means first image which gives us a fourth one. Okay, first mapping which goes to the fourth. Now we want the fourth mapping where it is goes. Now for that fourth mapping we have to check fourth column. Okay, first, second, third, fourth. Now you can see here fourth column which goes to first row. Okay, so we can write fourth column goes to first row. So I got the first order pair which complete here. Okay, how I found here we can see first column which goes to fourth row. Again, now if our first element end here, we have to find out another connected cycle element that can get to the another element. Okay, like we did it into the group theory. First goes to fourth. Now check where fourth goes. Okay, so here we can see first, second, third, fourth rows it is here, fourth row here. Now check where it is goes. Fourth goes to first column. Okay, so fourth goes to first column. Now similarly do it for the second column. Second goes to first, second, third, fourth, fifth. So second goes to fifth. Okay, second goes to fifth. And now check out where fifth goes. First, second, third, fourth, fifth. Okay, second goes to fifth. I got the first mapping here, that is second goes to fifth. Now check first, second, third, fourth, fifth. So fifth goes to second. Okay, so second order pair complete here. Okay, different another cycle complete here. Now let's check for a third goes to sixth. Third column it goes to sixth row. So third column it goes to sixth row. Now check where sixth column is going. Okay, first, second, third, fourth, fifth, sixth. Now sixth column it goes to third row. Okay, so this one is also getting completed here. Okay, consider we have the order of sigma here. Okay, we use order of sigma, which is a LCM of these different cycles. Okay, these are the LCM of these different cycle, first cycle, second cycle, and third cycle. Okay, so for finding LCM, so what is the order of first cycle? It is here 2, again 2, again 2, 2, 2, 2, and I want the LCM, least common multiple for all the different cycles. So LCM of 2, 2, 2 is always 2. Okay, so I got the order of sigma as a 2 here. Now let's consider our matrix which is a. Okay, so I consider our matrix is a. That means if we take a to the power matrix to the power this order of sigma, we will get the identity. Okay, so this can be written as like this step. Okay, so matrix a to the power order of sigma, which is equal to, always we get the identity. Okay, so a to the power order of sigma is a 2. That means which we get the a square, which is equal to identity. Okay, so a square is identity, means we have here a square which is equal to 1. That means a which is equal to plus 1 and minus 1. Okay, these are the required eigenvalue for our matrix. Okay, so for solving a question from our in the exam, so we have multiple other way that we can solve this question. But if you know the standard property, if it is a permutation matrix, you will get the directly plus and minus 1 eigenvalue. Okay, So most of the time these are the looking quite difficult exams questions in our exam, but in actual they do not. Okay. So for that you need to know some basic concepts, some standard type of the matrix. Okay. So here we can get this solution by multiple way. So I found it here, the way of order of different cycle. Okay. So I got the eigenvalue for our matrix, which is a +1 and -1, which shows that our option number A and option number B, which is a correct. Okay, so here you all can see, I solved this solution here. Okay, this is a sigma. I got the different order pair. Okay, so 4 goes to 1, 1 goes to 4, both are same. That's why I remove this one. We no need to use this, because meaning for this one and this one is always same. So I got the sigma and length of a different cycle of a sigma and their LCM, it is a 2 here. It is the power order of sigma identity. And finally I got the eigenvalue for a square. Okay, so a square is identity, and then why lambda square is 1? Because it is a Cayley-Hamiltonian theorem says that when we take every matrix satisfies its characteristic polynomial. Okay, this one is the characteristic polynomial, a square lambda square is 1. Okay, so every matrix satisfies its characteristic polynomial. This is a Cayley-Hamiltonian theorem, so I directly apply this one here, so you will get directly the eigenvalue. Okay, so I hope you all have understood my today's lecture, which is completely based on a linear algebra and eigenvalue with a special permutation type of matrix. So even after, if you do have any difficulty, doubt, let me know in my comment section. I will come up with some other videos. So thank you everyone. Thank you for my today's lecture.